Good afternoon, guys. Yesterday we completed the convective mass transfer, overall mass transfer coefficient, and we started our discussion on the basics of distillation. Today we are supposed to discuss, as you said, the designing and working of continuous distillation column, also known as fractionating column. So the idea of continuous distillation column is where we have more than one number of stages. Okay, so here if you remember what is stage means, stage is any space or region of the equipment or the vessel where the feed is going in and separating into two parts, liquid and vapor, and those liquid and vapor leaving the space are in equilibrium, are supposed to be in equilibrium. Okay, a stage is the region of vessel where the feed stream enters, divides into liquid and vapor phase, and those liquid and vapor phase are supposed to be in equilibrium. Okay, if the liquid and vapor phases are definitely in the equilibrium, then that is called ideal stage. If they are not in the equilibrium, but still liquid and vapor phase are forming and leaving, then that is the actual stage. Or you can say non-ideal stage, or you can say the real stage. I hope this part is clear to all of you. If it is clear, then please answer in which type of stage the separation will be more, ideal stage or actual stage. What do you think? Thank you, Gulshan ji. Ideal stage, wonderful, that's the correct answer, because in ideal stage equilibrium will be achieved and whatever mass transfer will occur till the equilibrium, that will be more. The net rate of mass transfer will be more in a case of equilibrium. So there was one topic called flash distillation. In flash distillation only one stage is there, and that's why, and there if the liquid and vapor leaving are in equilibrium, that is also known as equilibrium distillation. If you remember, either you can say flash distillation, you can say flash vaporization, also known as equilibrium distillation. But when we have more than one stages, that is continuous distillation, or you can say fractionating column. So there is a vertical column where we have a number of stages, and usually that is your choice where how you wanna represent the number of stages from top to bottom or bottom to top. So usually we prefer the notations from top to bottom. So this is the first stage, second stage, and so on up to the nth stage. Okay, or since it is these stages inside the column, so we can also term them as trays. How many type of trays we can use, that we will see. That I hope all of you know that sieve tray is the most common one. Otherwise they can also use bubble cap tray or the valve tray. Okay, and this type of feed, you also know that the feed we are introducing in the column could be the subcooled liquid, saturated liquid, partially vaporized liquid, saturated vapors, or superheated vapors. Okay, but here in general, suppose we are sending the liquid, saturated liquid feed, because usually we introduce the saturated liquid feed only. Okay, so the liquid part will move towards the bottom as the heat source is there, so some of the liquid will vaporize and we are supposed to get the vapors which will move towards the top. So here, as the liquid is coming downward, it will pass to a reboiler, and here we are supposed to get the some of the liquid is vaporized thanks to the reboiler, and the residual liquid, the remaining liquid, leave as bottoms, or we can say bottom product, let's say W. So some of the liquid which was vaporized sent back to the column just below the nth stage, and this stream which is going back in the column is called boil up stream. Okay, so these are the vapors which will move towards the in the column, and as these vapors will move from the top of the column, since the liquid feed was there, so product has to be in liquid phase as well, so we send these vapors to a condenser. Where these vapors get condensed and collected in a drum. That drum is called a reflux drum. So now you have the option to withdraw this condensate, the product, as per your convenience, how much product you want to withdraw. So some of the product we withdraw as a distillate, let's say D amount, and the remaining liquid we send back to the column at the top of the first plate, and that is called the reflux stream. And then this liquid again move in that column. So throughout the column at every stage when we are using reflux, okay, when you are doing the reflux, so in the column at every stage we have liquid and vapor both present. Vapors thanks to the reboiler, liquid thanks to the condenser and the feed. Okay, so here the section of the column above the feed is called rectifying section, and the section below the feed is called stripping section. And why? Because as you know, right, stripping means removal of solute from a liquid mixture with the help of gas. Absorption is removal of solute from gas mixture with the help of liquid solvent. So here this feed is going as a liquid in the column and these vapors are moving. So the vapors are supposed to recover the more volatile component A. If we have a binary mixture in the feed A and B, and suppose A is the more volatile component, so these vapors are supposed to recover the more volatile component A from this liquid feed, from this liquid stream. Okay, so that's why this is called stripping section, as we are recovering the solute, the A, the component A, from the liquid stream with the help of these vapors. And vapors are the product. Vapors will leave at the top, will have large amount of A. The vapors will be rich in A. Okay, so here these vapors which are rich in A, when condensed, so you can understand we are doing the total condensation. When this vapor stream enters the condenser, we are getting the liquid only. No other vapor stream is there. So this condenser is acting as a total condenser, where the total vapors are condensed or converted into liquid. So you can easily understand the composition of these vapors and this liquid will be same. Okay, and similarly the composition of reflux stream and distillate will be equal as well, because this is just a splitting, no separation at this point. This is just a splitting. of the liquid stream. So the composition of these three streams is usually same when we are operating with total condenser. You can say total condenser. Okay. So this liquid already have a large amount of A. When this liquid will come in contact with the vapors, so some more A, you know that if we have large amount of A, like it is like as we discussed the Reynolds analogy in some class. So you remember, if we have large amount of food, so we can, if we have large amount of money, so we can donate large chunks. Okay, but if we don't have any money, we can't make any donation. So this liquid stream has a large amount of A, so obviously it will transfer a large amount of A to these vapor streams. So the concentration of A in the vapor stream is getting increased. So the vapors are getting enriched in A. So that's why this is called rectifying section, also known as enriching section. Same process is taking place, but the name are different. Here the vapors have less amount of A. So we can consider them as pure vapors going and recovering the solute. But here vapors have sufficient A and they are getting more A with them. Okay. So I hope now it is clear to all of you why we name these two sections like this. Rectifying section and stripping section. Is it clear, guys? Yes. Okay, wonderful. So this is the idea of continuous distillation. So if it is clear to all of you, then wonderful. Now let's talk about the designing. So as a chemical engineer, we mainly do the process designing of every equipment, because for mechanical designing we can do only after completing the process designing, if you have the idea of designing of the equipments. Okay, so here in our syllabus we will talk about the process designing only. And for doing the designing of any system, process designing, you need three things with you. First, you should know the working concept, the principle, how the column or the equipment is working. Second, the material balance, and third, the energy balance. So here on this column, first we will do the material balance. Okay. How we can do material balance? That depends. Either you want to do the material balance on overall column or inside the column on the trace. Okay. So this feed, let's say F going in, having two components A and B, and A is the more volatile component. Number of stages 1, 2, let's say this is a small n. This is m minus 1. N minus 1, n. This is the reboiler. Here we are supposed to get the bottom products, also known as bottoms. W will have A and B both, but B will be in large amount and here the mole fraction of A is, let's say, XW. So for B it will be 1 minus XW, as you know. Here it is XF, so for B it will be 1 minus XF. This is the boil up stream going in the column. All these vapors will move to a condenser. One thing which all of you should understand, that here in the reboiler liquid is going and we are getting liquid and vapor both. So this is the partial reboiler, because it is not converting total liquid into vapors. It is converting only some part of the liquid into vapors. So this is called partial reboiler. And that's how you can understand the reboiler and condensers. There are two types of reboilers and two types of condensers: total condenser and partial condenser. Total condenser, which convert total liquid into vapors, total vapors into liquid, and a partial condenser, which convert some part of the vapors into liquid. So in case of partial condenser, liquid and vapor both streams will leave, and in case of total reboiler, all the liquid will convert into vapors. But for partial reboiler, some part of the liquid will vaporize and the remaining will be in liquid phase. So again here, vapor and liquid both streams will leave. So remember this, partial condenser and partial reboiler may also act as ideal stage. If these liquid and vapors are leaving the column, reboiler, are in equilibrium, this partial reboiler is also one stage. And if this is the partial condenser and vapors and liquid both are leaving and are in equilibrium, then the partial condenser will also be one stage. Okay, I hope you can understand this. Distillate D, having A and B, large amount of A will be there, mole fraction is XD. So for B it will be 1 minus XD. XF, XT, XW are the mole fraction of desired component A in all streams: feed, distillate and bottoms. And this is reflux, let's say L. So as we want to do the material balance here, so you can do material balance on in different ways. First, you can do for overall system. The overall loop, on overall loop, if you see, we have reduced the entire process into one block diagram. So this will be something like this. What is happening inside the system, we don't care. So that's how we can reduce the entire process into one block diagram. And here, whenever we do material balance, remember we do in two ways: one overall, second for component. And what is the material balance equation at a steady state? Rate of material in equal to rate of material out. Okay, for unit operations, as there is no chemical reaction involved, so no material will generate, no material will be destroyed or converted, disappeared. So simply at a steady state, material balance equation will be rate of material in equal to rate of material out. So here the overall mass mole balance will be F equal to D plus W. And similarly, component balance over A will be total A in equal to total A out. You must have seen the same thing in process calculation as well. Okay, after that you can do material balance on rectifying section plus condenser. Rectifying section plus condenser means this part. And for this part, if you will see If you try to break down the column, it will be like this. Okay, so here how we represent the notations, I hope all of you remember. See, if this is the nth stage, so the stream leaving this stage will be denoted based on the number of that stage. So this is the nth plate. So the liquid leaving the nth plate will be denoted by Ln, and the vapors leaving the nth plate will be denoted by Vn. Similarly, their mole fraction you can also represent like this, Xn, Yn. Okay, I hope you can understand this logic easily. This is the standard way to represent the streams. So here, this is the nth plate. The vapors leaving the nth plate, let's say this is the flow rate Vn, and the liquid leaving this nth plate will be Ln. Okay, similarly the mole fraction will be here Yn, and for liquid it will be Xn. Okay, so for this nth plate, the vapors leaving has the flow rate Vn, mole fraction is Yn. So we can say logically this is the nth plate. After that we will be having some n+1 plate. So the vapor which is entering on nth plate is coming from n+1 plate. So the flow rate of this vapor entering will be Vn+1 and mole fraction will be Yn+1. Okay, and the liquid which is leaving the nth plate has the flow rate Ln and mole fraction Xn. So here again you can do the overall mole balance. So here overall mole balance will be total moles in equal to total moles out. Total moles in because of these vapors and leaving because of this distillate and liquid. So total moles in Vn+1 equal to total moles out Ln plus D. Can you understand this overall mass mole balance for this section? Guys, is it clear? Okay, wonderful. Now similarly you can do the component balance for A. All these are the mole fractions for A. Okay, the desired component. So total A in equal to total A out like this. And here if you try to generalize, if you try to rewrite this expression, you can write it as Yn+1 equal to Ln over Vn+1 Xn plus D over Vn+1 into Xd. And this equation is called the operating line equation of rectifying section. The operating line equation of rectifying section. Operating line means the operational line, means the actual mass transfer, how the actual mass transfer is taking place. Similarly, if you see the stripping section plus reboiler, stripping section plus reboiler. So here overall mole balance will be total moles in equal to total moles out. For the stripping section, this liquid, this feed here, let's say this is the mth plate. This is the mth plate. So for mth plate, the liquid leaving will have the flow rate Lm, and after that we will be having m plus 1 plate, and before that we will be having m minus 1 plate in general. So we can say the liquid which will enter on this mth plate will have the flow rate Lm minus 1. That is equal to the total moles out. So moles are leaving because of the vapors, Vm and bottom, like this. So similarly you can do component A balance here. Total component A in Lm minus 1 into Xm minus 1 equal to total components out Vm into Ym plus W into Xw. उसे थोड़ा सा और जगह बना देते ताकि आपको समझना इजी हो. And here if you want to rearrange this, you can write it as Ym equal to Lm minus 1 over Vm multiply by Xm minus 1 minus W over Vm into Xw. So this is the operating line equation of stripping section. How mass transfer is taking place actually in a stripping section. I hope this is clear to all of you. So can anyone of you tell me what will be the units of every equation here? Like for mole balance equation we have this. What will be the units? Units of these mole balance equations. In SI system obviously, what will be the units for each and every mole balance equation? Not the operating line equation, the mole balance equation. Come on guys. Mole per second, correct. Moles per second. I told you molar flow rates F, D, W, LV, these are the molar flow rates. So flow rates, molar flow rate always in mole per second in SI units. So if this is the actual amount, not the rate, so you can say moles. But since these are the flow rates, so these are mole per second. Okay. What will be the what about the operating line equations here? These operating line equations, remember these operating line equations are dimensionless but not unitless. Okay, these operating line equations are dimensionless but not the unitless equation. Dimensionless means when you will write in dimensional form, molar flow rate, they will get cancelled. Mole fraction does not have any dimensions. Okay, so operating line equations are dimensionless equations, but not unitless. Why? Because it is moles of liquid divided by moles of vapor. We cannot cancel them. Okay, moles of liquid divided by moles of vapors. So remember this point. Now, can anyone of you tell me if I want to do the energy balance? So obviously, energy balance must be in joule per second, and we have the mole balance equations in mole per second. So how I can convert this mole per second into joule per second? What I have to do? See, energy balance is always easy. Material balance, if you can do material balance, you can easily do energy balance. Because the only thing you have to do is, you have to convert the material balance into energy balance. Now, how I can do this? If I multiply by this value, joule per mole, then you can understand it will be converted into energy. Okay. And what is joule per mole means? The molar enthalpy. Okay, molar enthalpy. So for every section, multiply by their molar enthalpies. Okay, if I want to do the energy balance here for overall system, remember, if you want to do the energy balance, okay, so some energy is involved in condensers, let's say QC. Some energy is involved in reboiler, let's say QR. Okay, and how that energy will be involved, you know that. In condenser, QC amount of heat is getting out, leaving, and in reboiler, QR amount of heat is going in. Okay, because I hope you already know that. So for overall loop, the energy balance will be total energy in F into HF. Mole balance equation was this. F equal to D plus D, overall mole balance. So overall energy will be total energy in F into HF is the molar enthalpy of feed. Mole per second, joule per mole, mole per second, joule per second now. Plus QR, heat going in the reboiler, equal to total energy out, D into HD plus W into HW plus QC. QC is the heat getting out from condenser. So this is the energy balance equation for overall loop. I hope it is visible to all of you. Is it clear? Can you understand this point? Yes. Similarly, for this part, rectifying section plus condenser, energy balance will be Vn plus 1 multiplied by Hv n plus 1, enthalpy of vapor, molar enthalpy of vapors on n plus 1 stage, equal to total enthalpy out, energy out, that is Ln into HLN plus D into HD plus QC. This is the energy balance for rectifying section plus condenser. Now for the stripping section plus reboiler, energy balance equation will be this. Total energy in Lm minus 1 into HLm minus 1 plus QR equal to Vm into HVm plus W into HW. This is the energy balance for the stripping section plus reboiler. Okay, so I hope all these things are clear to all of you. Now here one correction, not correction, but one point which all general when you will see the literatures. So the flow rates of liquid and vapor in rectifying section, they represent by LV, L1, L2, L3, L, V1, V2, V3. But for the flow rates of liquid and vapor stripping section, they use the notations L bar or L dash. One means L1 bar, L2 bar, L3 bar, or V1 bar, V2 bar, V3 bar, or similarly for dash. We will use the notations bar. Okay, as we are referring the book Gencoplis, so based on that we will use the notations. So for stripping section, the flow rates will be Lm bar, Vm bar, Lm minus 1 bar, Vm bar. Okay, so that we can differentiate between the flow, like if anyone say this is the liquid flow rate, where, on which stage, in rectifying section or stripping. Okay, so we should be able to differentiate that easily. That's why we are just make these small changes in the notations. Okay, so here now when we talk about the process designing, so there are several methods they can use to design the distillation column for the process designing. And in distillation column, the process designing means we want to find out the number of ideal stages required in the column. Okay, the total number of ideal stages required. So they can use McCabe method, Ponchon-Sevret method, distillation sequencing method, and number of methods are there. But as per the syllabus we have to deal with McCabe method only. So we will talk about the McCabe method now. So based on McCabe method, there are few points which all of you should remember. In McCabe method, first the assumption. The assumptions in McCabe method. The points we consider, we assume, the imaginary points we assume to simplify the designing. Okay, the first assumption is constant molar overflow of liquid on each stage in respective section. This assumption is also known as CMO, constant molar overflow. Okay, what is CMO? See, this is distillation column, this is some feed, this is the rectifying section, let's say. So here in the rectifying section they are saying if we have, let's say, 3 stages, so the liquid flow rate L1, L2, L3 will be equal. Okay, and let's say that is L. Now the question is how? Because on each stage mass transfer is taking place between liquids and vapors. This is the first stage, so we can assume the liquid entering on the first stage is coming from some zeroth plate. And what is the zeroth plate here? That zeroth plate is nothing but just the reflux. Okay, because the liquid is coming from flux stream, so that is L0. Flow rate is L0 here. And let's say all these flow rates are equal, L. That is the assumption. Now, how this is possible? That is possible only when we have equimolar counter diffusion on each stage. Now understand like this. What happens on first stage? Suppose the liquid leaving the first stage has 13 moles of A, 6 moles of B. So total amount is 19. It will enter on the second stage where it will come in contact with the vapors. Suppose the vapors have total flow rate 17, where we have 14 moles of A, or you can say 18 moles of A and 1 mole of B. Okay, or actually just simplify that, 12 moles of A and 5 moles of B. Now it is 17, yes. Okay, so the idea is A will move from liquid to vapor and B will move from vapor to liquid. So equimolar counter diffusion means if 3 moles of A are going from liquid to vapor, simultaneously 3 moles of B will go from vapor to liquid. 3 moles of A are going from liquid to vapor, so simultaneously 3 moles of B will go from vapor to liquid. So in that case, the liquid will become 10 moles of A and 6 plus 3, 9 moles of B. Total is 19. For the vapor phase, you can see we have 12 plus 3, 15 moles of A and 5 minus 3, 2 moles of B. Total is again 17. So that's how you can understand the equimolar counter diffusion on each stage. So that's why the liquid flow rate is not changing. And since liquid flow rate is not changing, so that means the vapor flow rate will also be equal. It will not change as well. So let's say that is V for the rectifying section. I hope it is clear to you. Similarly, for the stripping section, this is for the rectifying section. For stripping section, flow rates will be L1 bar equal to L2 bar, Lm bar that is equal to Ln bar. Let's say L bar. Similarly, the vapor flow rates will be V1 bar equal to V2 bar equal to Vn bar, Vm bar, let's say that is V bar. Is it clear, guys? Assumption. Yes. Okay. So because of this assumption, now what will happen? So just try to understand. In the column, here, yes, this flow rate, this V1, this was V1 because this vapor was coming from the first plate, so it will become V. This liquid was coming from the nth plate, Ln bar, so this will become L bar. This is the vapor entering in here, that is Vn plus 1. Vn plus 1 bar will become V bar. This L0 will be equal to L. Okay. So these things will happen. So over condenser, here V is going in the condenser. Here the liquid is L and D. Okay, so here on the condenser, if you do the overall balance, overall mole balance on the condenser, if you will do, it will be total moles in V equal to total moles out L plus D. Here is a term like people can ask how we decide like how much liquid we want to reflux back to the column and how much liquid we want to withdraw as a distillate. So that we can define with the help of a parameter known as reflux ratio. Can be denoted by R, and reflux ratio is defined as L by D, amount of liquid reflux back divided by amount of liquid withdrawal as a product in distillate. Okay, so R is L by D, and when you put this value here, so you can see V is equal to, instead of L you can write R times of D plus D, so you will get V upon D equal to R plus 1. Okay, similarly in case of stripping section, the amount which we send back as a boil up, the vapors, we define a term called boil up ratio. That is usually denoted by RV. That is the amount of vapors sent as a boil up divided by amount of liquid left as a bottom product. Okay, so again here if you will do the overall balance on the reboiler, you will get L bar equal to V bar plus W, and if you put the value of V bar here, that will be RV times of W plus W, so you will get L bar over W equal to RV plus 1. Okay, so with the help of these reflux ratios and boil up ratio, we can simplify the operating line equations. Okay, so for the rectifying section, the operating line equation was Yn plus 1 equal to Ln over Vn Xn plus D over Vn plus 1 into Xt. That was the operating line equation. So L upon D is, you can see, V upon D is R plus 1. So D upon V will be 1 upon R plus 1. And L upon V will become, L by D is R, V by D is R plus 1. So take these two ratios, you will get L upon V equal to R upon R plus 1. This is Xn. So this is the operating line equation for rectifying section in terms of reflux ratio. So one important point is, as per the McCabe method, the slope of operating line, if you know, this is a straight line equation in the form of y equal to mx plus c. So the slope of operating line will be, which was ln upon vn plus 1, will be equal to r upon r plus 1. And the intercept, which was vxt dxd upon vn plus 1, will be equal to xd upon r plus 1. The intercept. Remember this. This is the key point. Okay, because they can give you the operating line of rectifying section and then they can ask you what is the reflux ratio, or they can give you the reflux ratio, they can ask you the slope of rectifying section. So these are the things. This is the important point, key point here which all of you should know. The operating line equation, the slope, the intercept. And what is reflux ratio? Is it clear, guys? Yes, wonderful. Now similarly for the stripping section, you know that the operating line equation Ym was equal to Lm minus 1 bar over Vm bar Xm minus 1 minus W upon Vm bar into Xw. As per the CMO assumption, you can also write it as L bar over V bar Xm minus W over V bar Xw. And as we know, V bar upon W is RV. So V bar upon W is RV. So V bar upon W is RV. So you can write it as this. L bar upon V bar, you can see L bar upon W is RV plus 1, V bar upon W is RV, take the ratio, so you will get L bar upon V bar equal to RV plus 1 upon RV. This is Xm minus 1. So this is the operating line equation of stripping section. And again for a stripping section, operating line, so you can see the slope will be, which was L bar over V bar, that will be equal to RV plus 1 over RV. And similarly the intercept will be XW over RV. I hope this is clear to all of you guys. So this is something about the rectifying section and stripping section. Now the question is, how can we draw these operating lines? So for this, we use the XY plot. So for the reference, there is a 45-degree line, which is actually X equal to Y diagonal. Okay, X equal to Y line will be the 45-degree line, you know that. Okay, and the equilibrium, from the literature we can easily get the equilibrium data for every system, for any binary system. So let's say this is the equilibrium curve we got. Okay, so on mathematically, if I ask you, write down XF, XT and XW. So I hope you can understand that XF will be greater than XW but less than XD mathematically, if these are the mole fractions of more volatile component, because distillate will be rich in more volatile component A, bottom product will be rich in less volatile component B. So you can locate XW, XD and XF. This is XT, this is XW. Okay, so for the rectifying section, the equation is y n plus 1 equal to r upon r plus 1 xn plus xd over r plus 1. For stripping section, the same equation we can also write. This is for m minus 1 plate. Instead of this, if you use m plate, so this will become ym plus 1. So you can also write it as ym plus 1 equal to rv plus 1 upon rv xm minus xw over rv. Okay, so for the rectifying section, you can see xt. Slope is r upon r plus 1. As you know the slope, you can draw the line. That will be a straight line, and this point will be the intercept, that is xt upon r plus 1. This is the operating line of rectifying section. Similarly, for the stripping section, you have xw. So this will be the operating line of stripping section. Now people can ask you, this line is not starting from here, x-axis. For stripping section, the operating line is not starting from the x-axis, although it is starting from the xy diagonal, y. So any one of you have any answer? If you guys know the answer, just say yes. If you don't know the answer, just say no. Okay, don't explain, just say yes or no. Whether do you know why this operating line of stripping section is starting from diagonal, not the x-axis? This is the question. See, in case you don't know the answer, you can say no. You have choice. No problem. If you don't know, it's wonderful. At least I will be able to explain something to you, something new to you guys. What you have to do, just put x equal to xw. I want this point xw. So put x equal to xw here. When you put x equal to xw, it will be rv plus 1 upon rv times of xw minus xw over rv. And rearrange this, you will get xw. Y is not equal to 0. This is the operating line equation of a stripping section. So we know that in a stripping section, for this mole fraction of x, this will be the mole fraction of y in vapor phase. For this mole fraction x in liquid, we will be having this mole fraction y in vapor. So for the mole fraction xw, if you see here, Kangya, this is xw, these three compositions, but this is also from here only, from the stripping section. Okay, so this will also lie in this operating line. When x is equal to xw, y is also equal to xw, as you can see, and xw, and since this is x equal to y line, so this will be equal to xw, y on y axis. That's why here this operating line of a stripping section is starting from diagonal, not the x-axis. Is it clear now? No other reason. There is no other reason. Just this is just simple mathematics. Similarly, you can see for xd why it is the operating line of rectifying section is starting from xy diagonal. Here in this equation, just put x equal to xd. So equation will be this. So you can see y is equal to xd. So xt. So on x equal to y line, this value will be xt. That's why it is starting from the diagonal. Because in our system, for the liquid, xw is the least possible composition of A in liquid phase, and xd is the maximum possible concentration of A in liquid phase. Okay, and this is the separation which you want, the desired degree of separation. So we always know what should be, or we always know that xw and xt, their values, because we know how much separation we want. So we know that this much A should be, that the distillate should be 90% pure or 95% pure or 98% pure. That is the desired. Okay, so when we know the desired values, that's based on that we can do the designing. Okay, it is not possible to design a column without knowing xd and xw. हम अपनी मर्जी से कुछ नहीं कर सकते, like send just input and whatever output we will get, okay, we are happy with that. No, we always want output. Based on that we make the efforts. Okay, like you people also want the output. You know, you want some rank in gate exam, you want some marks in gate exam. That's why you are doing the efforts. Okay, you have some goal in your mind. Okay, that I need this many marks or I need this much of rank. That's why you are making efforts. Without having a goal, you can't make any efforts. Okay, I always use this simple example which we can relate everywhere. Suppose your younger brother or sister is coming to you and having board exams of 12th class science, obviously, and he or she is asking, I need only 60% marks. I just want to pass. So I just need 60% marks in my board exam. So what I have to do? What I have to study? You can easily answer, okay, just do this only, you will pass. But if your brother or sister is coming and saying, I want 98% marks, 99% marks, or 95% marks in my board exam, what I have to do? Then you will give some idea. So you can understand the efforts will be different. Similarly, when we know the output, only then we will make the efforts. In BTech as well, you must have done the same thing. There are many papers. Okay, we write almost more than 100 tests in the BTech exam, during BTech in those 4 years. So must be there is any subject or any test which you are not interested. Okay, you just want to get pass. So you don't make any extra efforts. You just read the important notes, or maybe without reading you just go for that exam. So this happens. But if you need some marks in any exam or any test, so you make efforts. You do study for a month or for a week. Okay, so it is like that only. Anyways, we will not go in all these things, as all of you already know what you have to do and what not. So again, come back to the point. Output is important, the goal is important. So based on that, we set up the things, the equipment, we do the designing. Okay. So are we clear with this, guys? Yes. Okay, wonderful. So I hope guys this curve is visible to all of you. So can you tell me what will be the reflux ratio and boil up ratio here? The values. Reflux ratio almost 2 and boil up ratio 1.96. Khushi reflux ratio 1.5. See, this is the operating line of rectifying section. Here they have mentioned the operating line equation is this. Means this is the slope. And what is the slope of operating line? R over R plus 1, that is equal to 0.667. So from here you can calculate R. That will be this. Almost. You can check. And similarly for stripping section guys, this is the operating line. This is the equation. So you know that the slope is RV plus 1 over RV, that is equal to 1.509. So on solving this you will get RV equal to 1.96. So I hope this is clear to all of you. So this is something about the rectifying and stripping section. Okay. Next we will talk about the feed line equation. Because in distillation column we have three parts. One is rectifying section, one is stripping section, and the third one is the feed plate. the inside the column, the tray or the plate on which we are introducing the feed is called feed tray, or you can say feed plate. Okay. And how can we find out that? That is easy. This is for rectifying section, and this is for stripping section. One thing you can understand that in a distillation column, this is the feed plate. Above this we have rectifying section. Below this we have stripping section. So that means the feed plate is the one which is dividing the rectifying section and stripping section. Also we can say that feed plate is common in between the rectifying section and stripping section. Okay. So operating line equation of rectifying section, operating line equation of stripping section, they are intersecting at this point. And this is the rectifying section and stripping section. So that means through this intersection point, feed plate must be related. Feed plate is associated with this point. Okay. And let's say this point is x comma y, because it is obvious. Above feed plate, rectifying section, below feed plate is stripping section. So feed plate will be common in these two. So the intersection point of these two stages will definitely have feed plate on it or something to do with that. So for rectifying section, if you remember, the operating line equation is yn plus 1 equal to r upon r plus 1 or you can write L upon V times of xn plus d upon V times of xt. For stripping section, ym plus 1 equal to L bar over V bar xm minus w over V bar xw. So for this intersection point, on intersection point, one thing is obvious that yn plus 1 and ym plus 1 are same, and we can say that is y, and xn is equal to xm, and that we can say is x. Okay, so the equations will become like y equal to L upon V x plus d upon V x d, and the second one is y equal to L bar upon V bar x minus w upon V bar into xw. And when you rearrange these expressions, I am not going to do the derivation, as all of you know that what is the derivation behind that. So when you rearrange these two expressions, and then you will reach on the final equation, that will be y is equal to q upon q minus 1 times of x minus xf over q minus 1. And this equation is called the feed line equation. And here this Q is called the quality of feed. Okay, basically it represents the fraction of liquid in the feed. In simple words, we can say the fraction of liquid in the feed. So if anyone asks you what is the slope of feed line, so you can see the slope of feed line will be Q upon Q minus 1. And feed line, this is XF, so you can put X equal to XF here. See, when you will solve, you will get Y equal to XF. This point is the XF. That's why the operating line of rectifying section, stripping section, and feed line, all they start diagonal only. So from here, the feed line must pass through this intersection point. So this is also one important question they can ask in interviews or in MSQ type things or MCQs. At this point, at this intersection, the operating line of rectifying section, operating line of rectifying section, operating line of stripping section, and feed line, all these three equations or meet. Okay, this is the point at which these three equations meet: the rectifying section, stripping section, and feed line. And the slope of this feed line is Q upon Q minus 1. Okay, what is Q? Q? In simple words, we can say Q represent the fraction of liquid in the feed. Okay, I hope this part is clear to all of you guys. So till now we have one, that is CMO. There are many assumptions, but mainly three assumptions are there. First is this constant molar overflow in each section. Second is latent heat of vaporization is same throughout the column. Means latent heat of vaporization is independent of temperature and composition. Okay, so the meaning is inside the distillation column on each stage the amount of heat required to vaporize the liquid, vaporize 1 mole of liquid, will be same. Third assumption is no heat loss outside the column. Okay. I hope this is clear to all of you guys. Now the types of feed based on which you can understand what is Q. Types of feed. So there are 5 types of feed. One is saturated liquid. Second is subcooled liquid. Third one is liquid plus vapor mixture, or you can say partially vaporized liquid, or you can say partially condensed vapor. Fourth one is saturated vapor, and last one is superheated vapor. So Q, you can also write it as L minus L. If I talk about the actual definition of Q, it is the amount of heat required to vaporize vaporized 1 mole of feed completely divided by molar heat of vaporization of liquid. You can understand, like suppose in we have two containers filled with liquid water at 1 atm pressure. In first container the temperature is 78 degrees Celsius. Here the temperature is 25 degrees Celsius. Now this is the second container. We are supplying the heat to these containers. So what do you think, guys? From which container the vapors will start to form at first place? First or second? First one, correct. So if I ask you the amount of heat required to vaporize the liquid, okay, here it is Q1, here it is Q2. So which one will be more? Q1 will be greater than Q2 or Q2 will be greater than Q1? What do you think? I want to convert this liquid into vapor completely. Okay, complete vaporization. So for that, Q1 will be less than Q2 or Q1 will be greater than Q2? What do you think? Q2 will be greater than Q1, obviously. Correct. So here make it saturated liquid. Okay, for the saturated liquid in the definition. Now it will be easy to understand. If I say there is a third container having liquid water at 100 degrees Celsius only. Okay, so and here the heat involved was Q3. So now Q3 will be less than Q1 or Q than Q1? Less, obviously, because this is already a saturated liquid. So what we just need to supply the latent heat of vaporization. Here latent heat as well as sensible heat. Latent heat plus more amount of sensible heat. Okay, so there, based on that logic, I hope you can understand now. For subcooled liquid, Q will be less than 1. Saturated liquid, only this. This is subcooled liquid. Any liquid mixture below its bubble point temperature is subcooled liquid. For saturated liquid, Q will be 1. Because if liquid feed is already saturated, feed is already a saturated liquid, so this ratio will be 1. If we have a mixture of liquid and vapor, then Q will be less than 1 but greater than 0, because some liquid is there. Total liquid nahi hai. Some liquid is there and some vapor. For saturated vapor, when feed is already a vapor, so Q will be 0. And if superheated vapors are there, Q will be greater than 1. And based on the logic, like I told you, in layman terms, we can say Q represent the fraction of liquid. Okay, so saturated liquid means total liquid, so Q has to be 1. Okay, fine. Saturated vapor means all vapors, no liquid, so Q is 0, that is also fine. But why these three conditions are there? liquid plus vapor mixture, okay, that is also fine. Some liquid, some vapor, Q is between 0 to 1. Okay, correct. But why these two? Why these two? We have made it wrong. For subcooled liquid, we need more heat. So Q will be greater than 1. And here it is less than 1. For superheated vapor, tell me, it should be less than 1 or less than 0? What do you think, guys? Correct. It should be less than 0, otherwise there will not be any difference between partial vaporized and superheated. Why so? Because just try to understand, this is the feed plate where we are introducing the feed plate. Okay, some liquid is coming from the rectifying section due to reflux, flow rate is L. Liquid will go in the stripping section, L bar. Some vapors will come in from the stripping section thanks to reboiler, and some vapors will go in the rectifying section, V. Now, just try to understand, if this feed is subcooled liquid, this one. So what will happen? This feed is subcooled liquid. This feed will go as it is in the stripping section. But since it is subcooled, so whatever vapors will come in contact with this feed, some part of those vapors will also get condensed. Okay, because here if you write the material balance, it will be like L bar equal to L plus F, and V is equal to V bar plus F. Based on that, it will be Q times of F. It will be V equal to V bar plus 1 minus Q times of F. Okay, this will be the better balance. Q is the fraction of liquid. So when feed is subcooled liquid, that is going in the stripping section, along with that it will condense some part of the vapors here. So you can understand the L bar will be L bar for first case. L bar will be greater than L plus F. L bar will be greater than this L plus F. L plus F. उससे भी ज़्यादा होगा यहाँ पे जो liquid है, because some liquid is coming from these vapors. Okay, so that's why you can understand, if L bar is greater than L plus F, it means Q has to be greater than 1. Okay, that is another way to understand Q. values. If saturated liquid is there, so you can understand whatever liquid is going as it is, it will go, it will not disturb vapor, it will not disturb the reflux liquid. Okay, so L bar will be equal to L plus F, simple. So Q will be 1, no problem. If it is a mixture of liquid and vapor, then whatever feed you are sending, some feed will go in the here, and some feed, the vapors, will go in the rectifying section. Okay, so L bar will be L plus fraction of liquid coming from this multiplied by F. V will be equal to V bar plus fraction of vapors coming from this feed multiplied by F. So L bar will be equal to L plus Q times of F. Simple, no problem. Okay. So Q is in between 0 to 1. You can easily understand for this. When saturated vapors are there, because why? Because remember this, whenever feed is whenever feed is mixed, that means, if you remember the TXY diagram we discussed yesterday, this part is between these two. So this is two-phase region, but saturated mixture, saturated liquid and saturated vapor. Okay. Saturated vapor as it is will go on this side. So V will be equal to V bar plus F, no problem. So here L bar will be equal to L. So Q has to be 0. Okay. Because whatever feed we send as it is went into the rectifying section. And superheated vapors. Now again the logic, when we have the superheated vapor, they will go in the rectifying section and simultaneously they will vaporize some part of the liquid coming from this reflux liquid. Okay, so you can understand that V will be greater than, here V will be greater than V bar plus F. That's why Q has to be less than 0, a negative value. V will be greater than V bar plus F only if Q is negative. Okay, so that was correct. Q will be negative here. Okay, so that's how you can understand these values in this terms, in terms of nature of the feed. I hope all these things are clear. Now, what is Q actually, and how you can find out the values of Q and something. And remember the slope of feed line equation, Q over Q minus 1, and the intercept is XF over Q minus 1. Is it clear, guys? So remember, all this explanation was possible only because of the second assumption. Okay, we are generalizing all these things for the entire distillation column because of the second assumption. Second assumption was of McCabe method. The latent heat of vaporization, or you can say the molar heat of vaporization of the liquid, will be same throughout the column. Okay, it will be independent of temperature and composition, as we have seen in that example. I don't know. Liquid at 20 degrees Celsius, liquid at 80 degrees Celsius. So you know that amount of heat required to vaporize this liquid completely will be different in these two. So molar heat of vaporization will be different on different temperatures, that is obvious. But the assumption is it is independent of temperature and composition. We don't care what is the temperature of the liquid on the stage, but it will be same. That is the meaning of second assumption. Is it clear now, the second assumption, to all of you? What is second assumption and the significance of that second assumption and the importance in McCabe method? Yes. Okay. So this is it for today. The next is how to find out the number of stages in a distillation column and the operating conditions in distillation. Okay, operating conditions like if we increase the reflux ratio or if we decrease the reflux ratio, some conceptual part, and after that we will discuss the numericals. Okay, so that's all for the day. If you guys have any specific numericals related to distillation which you want to discuss from GATE previous year papers, like this question must be discussed in the class, so you can send me, you can send that on your WhatsApp group, okay, or you can send that to the office numbers or Lalaji, they will connect you. They will give me that and we will discuss those questions in the next class. So see you guys in the next class. Have a very good weekend. Not here, Swapnil, to Lalaji or in your group. Okay. So see you guys on Monday. Then till then, bye bye. Take care. Stay safe. Stay healthy. Tada.